vehicle and the intro slide, correct?
Yes.
The agenda for tonight, I think I wrote 8 p.m. That's a mistake. It should be 7:30. Apologize for that. A little bit of housekeeping. Other than the speaker, please keep yourselves on mute on your webcams, except when speaking or asking questions. I'll give a little bit of an overview of SAE I'm the chairman, Colin Ketty. I will introduce Polly and her presentation for aeroacoustics problems and modeling challenges in electric vehicles. I just want to mention our next SAE board meeting for anybody who's interested in maybe sitting in and seeing how we do things is next Monday, April the 3rd. We do those online at 5:30 p.m. It usually takes about an hour or so. Our next SAE event after this will be towards the end of April. April 24th, we have Wago Wang on a discussion regarding reverse engineering, which I think is applicable to just about anybody. Our entire calendar of events is on our website at saebritishcolumbia.org. And for all of our communications and information, we have our SAE newsletter that we send out to our members who are signed up for that. As well, we have the website, and we're on social media on LinkedIn, Twitter, and Instagram. I just want to talk a little bit about some of the benefits of SAE. There's three main benefits for attending and participating in SAE. The first one is the biggest one is networking and career development, especially for the younger audience out there. For any of you who want to, get a foothold in maybe a new industry, it's a good way to network and develop your career that way. We also have the SAE Gold List. This is a list of all the active mobility related companies in British Columbia, and you can find that on our website. And the third reason is that it's interesting and fun. I mean, I think we have some really great speakers, and we've had some really great topics in the past, and I'm looking forward to tonight's topic. We have a few open opportunities on the board. We have a vice chair and newsletter. We could use some website support for anybody who's web savvy. As well, we're looking for a secretary and even just general support. We can tailor roles for people if you just want to help out any way you can. And the benefits are, career networking and building up your resume, especially for the students coming out of school when your resume may look a little thin. This is a good way to boost your resume a bit. Everyone appreciates volunteer work. And we look forward to your feedback and support. You can check out our website. On there, you can find a link for info at saebritishcolumbia.org if you have any questions or any general comments. And that's about all I've got. I would like to introduce to Polly. I'm sorry, I'm going to butcher your last name. How do you pronounce your last name again?
Dhodke.
Thank you. Her mission is to make the world free from unwanted noises and achieve more peaceful, quiet, and calm life for everyone. In terms of experience, she's been the lead engineer for automotive giants in India like General Motors and Tata. She has 15 plus years of industrial experience, specializing in aeroacoustic modeling. She's an expert in CFD process development and aerodynamics, thermal management, in-cabin airflow, aeroacoustics, and data science projects. She has published work in supersonic to low subsonic domain. She is a PhD in mechanical engineering with a master's in space engineering and rocketry and a bachelor's in chemical engineering. She has 4 copyrights and 6 international publications. So without further ado, I will stop sharing and turn it over to Polly. Thank you very much.
Thank you, Colin. The screen is visible to everybody.
Yeah,
Is
it's
it
coming through. Thank you.
okay? Good. So yeah, thank you, Colin, for this opportunity, and I'm glad to present this topic to SAEBC community here. So with the electric vehicles, there are a lot of aeroacoustic challenges that are coming up, and this is what I thought of picking up this topic and making aware of everybody uh, why the noise is important. What are the new noises that are being introduced to us with this electric vehicle development? The brief history and some physics and mathematical background about flow-induced noises. So aeroacoustics can also be called as flow-induced noises. Then we can look at how we can model them, different solver approaches, and there are different noise source identification methods as well that I'm going to present. And at the end, we'll go through a few case studies that are related to the automotive industries. What is noise basically? Previously the noise is mainly identified as a sound and that are used to pick some life threats or life sources in our life. But with the technological advancement, uh, we didn't knew that how this sounds has been converted into noise, and then we are exposed to different noises throughout our day and night, and that are creating a major problem in our modern life. When we look at the noise pollution data from Environmental Protection Agency, they have plotted for different noise levels like urban traffic to air traffic to industrial noises. And we say that the urban traffic is affecting more than 100 million people, whereas the loudest noise is affected with zero point 0.1 million people. And the urban traffic is spread all over the noise level from 80 to say 50 dB, and these are the noises that we are continuously exposed to. Secondly, the second most noise source is the aircraft noise, and we see that the noise level generated is also significantly high. But if you look at the size of these bubbles, they are lower. That means the population affected by these noise level is relatively lower than the urban traffic. And when we look at the rail noise and the industrial noises, they are also relatively low. So so this plot shows that the urban traffic is affecting wide range of people, and that can be really looked into if you want to improve people's life. So when we look at the noise pollution and how it is spread throughout the environment, the noise is nothing but a disturbance that propagates through the elastic medium such as air or water. And usually noise is nothing but an unpleasant sound. So for example, when a vehicle is traveling, it generates a noise, and that sound will propagate through the air, and then it is received by the receptor or receiver. When we look at the physics involved in the system, we see that the noise is nothing but a pressure wave or wave where the density of the medium changes. And when we look at its physical properties, noise and sounds share the similar ones. So the amplitude of the pressure is nothing but the variation of the pressure over a hearing threshold. So our hearing threshold is 2e minus 5 Pascal, and the frequency is nothing but when we fix the point at uh, one particular position, and the number of waves that are passing through in 1 second, that we call as frequency. whereas the distance between the two peaks or two peaks or two troughs, we call them as a wavelength. So this is the basic sound or noise property we can refer to, and that is very important when we go forward in this presentation. When we look at, as we know that the urban traffic is the major noise source, and when we look at the different noise sources that a car is generating, we can see there are multiple noise sources, majorly coming from the IC engine, the intake noise, the gear noise, rattling noise, exhaust noise, road noise, and there are some flow-induced noises such as radiator fan noise, wind noise, some AC noise. So until now, or until the recent development of electric vehicles, in IC engines, the major noise is generated by the engines and all other noise were masked. But with this electrical vehicle development, the engine is gone and all those conventional noise sources have been removed. So until now, all those mask noise sources have been popped up. And now we see that the radiator fan noise, AC noise, wind noise, road noise, and the rear AC or blower noise that are becoming a dominant noise source in an electric vehicles. So road noise is not completely a aeroacoustic problem, but it is a partially aeroacoustic problem. And apart from that, there is a new challenge that is coming up, is the fast charging stations. So now the requirement is we want our car to be recharged or charged very quickly, and that demands a very high fan RPM, and it's because the heat produced by the batteries need to be cooled down quickly. So the high fan RPM are producing a lot of noise, and that is one of the upcoming noise sources, I would say, or it is already entered in the market or people's life. Still, the noise is concerned because, according to the British Medical Bulletin, the noise cause the permanent hearing loss, the distress, hypertension, and cardiac diseases. Apart from these health problems, it is very important right now for an OEM to achieve the noise comfort, because all other comfort has been addressed and customers are asking more about the noise comfort inside and outside the car. So that's why it is more important for any OEM to develop such a solutions. Secondly, to before launching of the vehicle, the OEM has to pass or qualify the pass by noise certification. So now the engine and exhaust noise that are gone. So all the other mass noise like radiator fan noise, um, or other noises that are bothering the customer, that need to be reduced, and the pass-by noises like radiator fan noise, that need to be reduced to qualify the EPA certification. And thirdly, now the competition is very big, and with the leading technology, only OEM can beat this competition. So therefore, noise is a very concern, and it's now more asked by the customer feature for any vehicle. When we look at the typical noise spectra or typical noise stress, we can get a pressure versus time wave, and this pressure versus time history doesn't give us much of the information. But when we take a Fourier transform of this pressure wave, we get something like this. So this is a typical spectra that we can get from any source, for example, radiator noise or wind noise. So this plot is mainly for the fan noise, because we are plotting here blade passing frequencies. So the blade passing frequencies are heard at every blade rotation. So that's why we see these peaks, and these are the different harmonics of that blade passing frequency that is shown by green curve. whereas there are some subharmonic hums, so there are some disturbances that interact with the fan blade, but they are not traveling with the fan RPM. So we can hear those frequency in between the two BPF peaks. So this is what we call that as a subharmonic peak. Whereas there is a broadband noise. So broadband noise is nothing but a random noise that can be heard all over the frequency spectra. And this broadband noise basically decides the shape of the spectra as well as level of the spectra. So if the broadband noise is lower, all those peaks and subharmonic peaks will go down. So this broadband noise really plays an important role for identifying amplitude of any noise spectra. And then there are some high tonal peaks that can be observed, but this is somewhat rare in any automotive problem, because mostly all our noise, uh, all the flow behaviors are turbulent, and the high frequency tonal noise is not really observed in this case. It is mainly observed in laminar separation bubble, where the when we have like um, cusp trailing edge, where we have some laminar and flow, laminar separation bubble, and this trailing edge noise interaction. There we get sometimes the high tonal noise. So when we look at the different noise sources, we can categorize them in different forms based on the way they propagate. So monopole is nothing but a single noise source, and its wavefronts are traveling in all direction. And if we take amplitude at any one wavefront, the amplitude does not vary. It will remain constant along any wavefront. And this is a typical example of volume fluctuations, where, for example, in our real life example is the loudspeaker noise. So that is a typical example of a monopole noise source. And if we plot its directivity plot in all 360-degree, we will hear the single amplitude. Secondly, the dipole source. So dipole source is nothing but two monopole source placed at a position, but they are in out of phase. So if this is in a positive phase, the other one is a negative phase, and vice versa. And these dipole sources basically propagate parallel to their fluctuation, and we see that the noise cancellation will happen in the normal direction of their fluctuation. So in this case, when we record the noise, we will have a different behavior than the monopole source. As I mentioned, at 90-degree and 270-degree, we won't hear any noise, whereas the noise will increase towards the center, about 180-degree or 0-degree. This is this dipole source is mainly observed in a wall pressure fluctuation. When we look at the quadrupole source is nothing but two dipole source placed at the same time, and we can also see the different behavior when we plot its directivity. Again, we see some noise cancellation effect in these areas, whereas there are peak amplitude that has been heard in the direction of its propagation. So why we are talking about these sources here? Because, for example, if it is a monopole source, if we put our microphone at any location, we will hear the same amplitude. Whereas if we put our microphone for any dipole type of source at say 90-degree, we won't hear any noise. So therefore, the knowledge of the source and its directivity pattern is very important while we are recording any sound. So basically, noise is or sound is recorded in any anechoic chamber. So anechoic chamber is nothing but the room is filled with the wedge-like shapes where uh, they are like a sound absorbing material. Even the floor is also filled with such type of a structure. Here we cannot see it because the mesh is provided so that people can walk on it. But but the wedges are present below this mesh. So this setup is usually usually expensive for any full vehicle testing. So most of the time the floor is a hard wall, and the remaining walls are has been modified with this wedge-like sound absorbing material. And again, you see that uh, these gentlemen are measuring the noise, I think motor noise, and you see it's not just a single microphone placement, it's multiple microphones that they have placed. So they are making sure that the directivity has been captured so that they can capture the noise level in each direction and calculate its or measure its signature. Secondly, if it is a wind tunnel type of a source, there multiple background noise sources are present. So, for example, you have some dry fan systems. Then, if these microphones are mounted inside the airflow field, then you get some self noise generated due to strut mounts or due to the microphone stands. Thirdly, there is the airflow is directed through the air duct, so that air duct also creates some noise due to the airflow turbulence. Fourth, if there are some plain walls as we speak about, like the floor, that if that is a plain wall, that can also generate some boundary layer, and that boundary layer can radiate some broadband noise. So, so it is very important to measure the background noise before we start reading any before we start taking any measurement. And as I said, the microphone placement is very important to capture the directivity effect. And then there are like near field effects and the far field effects too. Um, if it is a semi-anechoic chamber, then the reflections can occur from the ground. So we have to make sure that sufficient distance has been maintained between the source and the ground so that we don't get high frequency reflection. Of course, there are some low frequency reflection that we cannot really omit. Secondly, the tonal noise is really really sensitive to such reflections if you want to capture that noise correctly. So we need to take care of those things also. And there are other sound interference. Like this lab really looks very clean, but I have visited few automotive labs. Like they have multiple solid objects that are present inside the lab, and that object can create some scattering or reflections that can create some interference, and it can modify the noise signature. So it is very important to keep the room clean, and we have to make sure that we are accounting all these different effects that can come into the measurement and that can pollute our measurements. So just for an example to give you an experience of what a wind tunnel look like and how these acoustic measurements are done for a full vehicle level. This is the recent automotive lab or wind tunnel that is set up by Honda. It's like 124 million test bed, and it can measure up to 200 miles per hour wind speed. So for that, the setup is very big, and we can go through its video. But before that, we can see how does it operate. So there they have this main fan. That fan pulls the air, and basically it throws the air in the settling chamber. The settling chamber is meant to reduce any recirculation or turbulence or non-uniformity that has been formed by the fan wake. So this settling chamber try to make the floor more laminar and uniform. Then it is very important to keep the air temperature uniform and at constant. For example, here the at ambient temperature is because the speed of sound varies with the temperature. Therefore, to have a consistency in the measurement, they have used these heat exchangers where they try to condition the air at a given temperature. Then there are some guidelines to avoid the corner separations, and from turn 3 to turn 4 the flow enters in the nozzle section, and from nozzle section the flow the flow blows over a test section, and in test section they put the car over here, and then there is some control room to adjust the speed, the wind speed, and all other factors. So this setup is also has a moving road facility where they simulate the road running thing with the belts. So yeah, that's all. And this is a closed loop tunnel. So again, the air is sucked by this diffuser like section, and then it is again sucked by this fan, and then uh, this loop goes on. So this is a typical example of closed wind tunnel, but there are some setups that operate with open wind tunnel also. So so we can look at how the aeroacoustic testing is done in this setup.
Let's do that now. So we talked about a couple different things this wind tunnel can measure, and one of them is acoustics. And it's acoustics of the wind going around the car. Is that correct?
That's correct.
And this is an array of microphones that you call the acoustic array.
That's right.
How does this work? How many do you have? What do you do with them?
There's 500.
So make sure that the amount of microphones that they are using while recording the noise here. So these microphones not only provide the pressure versus time trace, but these microphones are also useful in identifying the noise sources.
102 total microphones with all of the arrays we have here. We can measure the top, both sides, and the front of the car. We can identify not only how much sound is coming from the car, but also where exactly it is coming from.
And we talked about earlier, this would be really good for like accessories, roof racks or spoilers or anything where all of a sudden there's a sound and they don't know where the sound came from.
That's correct. The whole point of these arrays is to quickly give the engineer all the tools he needs to identify where the noise is coming from and how severe it is.
When it comes to acoustic wind noise, there's a camera that I'm speaking into now, and all those microphones around me, and I want to see what it looks like in the control center when I'm speaking. So I'm at a normal voice now. I'm going to raise my voice to a much louder voice to see what it looks like in the control room, and the colors should be changing in my voice right now. And as I bring my voice down, I'm going to bring my voice down to a quiet whisper and see if I can get my voice to still be heard and to see how blue it is. So that should be a test from very, very quiet to a little bit louder to a little bit louder to a little bit louder to a loud. How cool is that?
So yeah, that is called the acoustic camera technique, where it identifies from which direction the sound is coming, and it helps to localize the noise sources. So before that, we can look at just a small physics about how microphone record the sound, and then we can go about other noise source identification techniques.
How do microphones work? Though they have their differences and different uses, they are all transducers, converting sound waves to an electrical signal. The dynamic microphone is the most common used. These work using electromagnetic induction. Sound waves hit a thin diaphragm, which causes it to move. This diaphragm is attached to a coil surrounded by a magnet. This magnet creates a magnetic field around the coil. The sound waves hitting the diaphragm are moving the coil, and the coil's movement past the magnet creates an electrical current. This electrical current is your sound signal. Loudspeakers work in reverse. Here, the incoming sound signal moves the coil, which in turn moves the diaphragm, creating sound waves. Want to learn more? Subscribe or check.
So yeah, like as we saw, that the noise is nothing but the pressure fluctuation in a calm environment, and that has been recorded through the pressure transducer. So another technique is the beamforming. So beamforming is what we saw in this halo tunnel, in Honda tunnel, where they have multiple microphones set up at different locations. So what it does is basically it measures the time at which the sound wave is coming, and since the source is located at different distance from the microphone array, and the sound is traveling with a constant speed, so the noise that is arriving at these microphone reaches at different times. So when we calculate the time delay between these microphones, we can identify from which direction the noise is coming. Uh, so this is in short a beamforming method. We can look at how acoustic camera is also used. So acoustic camera is again based upon the beamforming method, whereas in this technique we can just use a mathematical operations to look at from where the noise is coming, whereas we can integrate mathematical technique with the actual images, and from that we can identify from where noise is coming and what is its amplitude.
Let's check out a real car measurement. The air arrives from the front. The two side mirrors are the obvious noise sources. But if we yaw the car a little bit to one side, we see an effect on the main radiating areas. The right mirror is less noticeable, while the left mirror area gets an additional noise source from the A-pillar close by. This effect increases the more we yaw this car. Let's turn in the other direction. Here we have the situation again with the car into the wind at 0 degrees, and the noise is radiated from both mirrors. But when we yaw a little bit further, we see how the wind against the A-pillar becomes the dominant noise source. Let's summarize. Both systems use the same software and therefore
and then we can put some pressure sensors like surface pressure microphones, and then we can try to correlate between the surface pressure microphones and the far field microphones. Then there is other method to identify from which direction the noise is coming. So we can have near field microphones as well as far field microphone, and that will help us in noise source identification. So these are the methods that are used in any test setup. So just to give an idea, a one-day testing at wind tunnel for full vehicle will cost around $70,000 to $80,000. And another limitation, like it is expensive. Secondly, the second problem is we can test the noises once the vehicle is built. And once the vehicle is built, going back and doing any design changes is next to difficult. And that's why the simulation plays an important role here. So before going through the simulation methods, we can identify which are the aeroacoustics method that can be used in any simulation. So the aeroacoustics is nothing but the branch of acoustic where the noise generation is studied, and the noise generation happens either due to the turbulent fluid motion or some aerodynamic force interaction with the surfaces. Or sometimes we see some periodically varying flows. For example, some vorticity shedding. So that is one of the example of periodically varying flows. And these noises can be modeled either with direct method or second with the hybrid method, and we can look at its pros and cons in coming slides. So direct method is that where we put all the microphones around the source, and these microphone is included in a computational domain. So the pressure wave or the pressure fluctuation that is traveling from source to the receiver, that is modeled in this domain. One of the advantages, like if there are any object that is present in between the source and receiver, and if they are causing any scattering or reflection effect, that has been properly captured in this type of simulation. The noise prediction accuracy is very good. I have done a couple of simulation with direct acoustics, and believe me, the prediction is on top of the test data. So it is really good, accurate method if when it comes to predict the accurate noise levels. Whereas this method requires large computational time as well as big computational domain, because we need to include the microphone sources, microphone receivers inside the domain, and based on the frequency of interest. For example, if you want to capture the high frequency noise, then we need to solve this equation at very low time step. For example, like 2e minus 5 second of time step. And if you want to capture the low frequency sound, for example, around 100 hertz, then we need to simulate it for almost for a larger time, so that we can capture that 100 hertz frequency resolution. So again, it is as I said, it is computationally expensive, but we can play with the cost and the accuracy based upon which frequency region we want to identify. We can go and we can reduce the time step and focus on high frequency region, or we can increase the time step and focus on a low frequency region if that is our field of interest. So the hybrid method, so the Lighthill has come up with the analogy, and he has done it in 1950s, where he identified that we can decouple source and receiver. So once we have a knowledge of source, we can use a simple wave equation to propagate that source in a far field. So the benefit of this method is we just have to focus in solving the equations very close to the source, whereas we don't have to model receiver domain, and here it saves a lot of time as well as computational effort. Only thing is that if there are any object present between the source and receiver, that cannot be accounted. So we cannot account for any scattering or reflection effects here. But this is a very, I would say, very useful addition by Lighthill, where we can model multiple problems with this analogy. So what does analogy says? So when there is a jet coming out of a nozzle, we see that these big blue and red patterns that are observed here, they are nothing but the acoustic waves, and they are traveling in this direction. So when we put a receiver over here, if you want to use the direct method, we should model the whole computational domain. Whereas Lighthill analogy tells us that we can model just a domain very close to the jet region, and that will give us the source. So this source is nothing but it's called as Lighthill tensor. And then once we know this source, we can use this wave equation to propagate the sound. So this has been, so this is the basis of the analogy, and it's a typical example of any non-homogeneous wave equation. So, so Lighthill analogy was very limited to high Mach numbers, and for only jet flows, where there is the noise is mainly generated by the turbulence produced by this jet flow. But the engineering problem is not only limited to this jet flows, but there are always some surface interaction, or sometimes the surface is rotating. And that's what Curl has added, extended Lighthill analogy, and he introduced a surface in the flow field. And now he come up that the noise propagated in the far field is the result of lift fluctuation caused by the incoming flow. So once we know the lift fluctuation, we can propagate it to the far field using the same non-homogeneous wave equation. Secondly, Flock-Williams-Hawkins analogy identified that there is a need of including the rotation to these surfaces. Therefore, they modified the equation so that we can account for the rotating machineries as well. And this is the final expression for the Fox-Williams-Hawkins analogy, where you can identify that it is consist of different sources, like quadrupole due to the turbulence formulation, dipole due to the surface pressure fluctuation, and monopole due to the volume fluctuation. One thing to be noticed here from the Lighthill analogy to Flock-Williams-Hawkins analogy is that 1 minus MR factor. So this 1 minus MR factor is nothing but a Doppler factor. So we can look at what Doppler factor is. So when the source is fixed, it will propagate the, so this is a typical example of monopole source fixed in a space, and that is propagating sound waves in all direction equally. But if the source is moving, the way sound waves are propagating are completely different. So previously, the sound waves are propagating with a constant speed, that is with the speed of sound. Whereas here, you can see the receiver is in this standing here, and the vehicle is approaching towards the receiver, and the collection of these wave fronts are happened because now the sound waves are not traveling just the speed of sound, but they are traveling with the speed of sound plus speed of the vehicle, and that's why we see that the wavefront are kind of collapsed, and they are traveling together. And here, again, the wavelength and the frequency is changed when the receiver is hearing that noise. Whereas if we put a receiver at the back of the car, the story is completely opposite. The wavelength is increased and the frequency is also modified, and that's why the noise heard by the receiver behind the car is completely different than the receiver in front of the car. And this change in this noise propagation behavior is nothing but the Doppler effect. So now we understood the direct method and the analogies that has been used, and the analogies adapted for the surface and the moving surfaces. So there are other methods also present, which are called as integral method. So in integral methods, so one of the method is Lie. So it is short form of linearized Euler equation. So it's the same phenomena that instead of modeling the whole computational domain, and we can model just the domain very close to the source. And now only difference is the way we are propagating the noise is different than the analogy. So analogy is the analytical solution of the non-homogeneous wave equation, whereas here we are using the linearized Euler equation. So inviscid, we are solving the wave propagation on an inviscid domain, and so this makes the computation relatively cheaper when it comes to the direct method, whereas this has a disadvantage that it needs a very small mesh when it comes to the high frequency noise recording. Then next is the control surface method or Kirchhoff method. In Kirchhoff method, the pressure fluctuations are measured on the control surfaces, and then these pressure fluctuations are again are solved numerically, so that we can identify the noise levels at the receiver ear location. And this method is suitable for the fixed medium where the medium of propagation is not moving. But there are a solution that has been given by Goldstein and all, where they provide the solution for the moving medium also. So we can use, so we understood how we can propagate the source, but now we can look at how we can model the source. And to model the source, there are multiple methods present. So the one method is the if you want to have a really accurate calculations of the flow field, then we can always go for direct numerical simulation, where we can solve 3D unsteady compressible equation, Navier-Stokes equations. But only thing is it requires a very large domain, and huge computational cost is involved to solve such a large domain. So, and still, although with the given cloud computing advantages and all, we cannot still use direct numerical simulation for any industrial problem. It is still limited to any academic research problem. But another alternative is the large eddy simulation. Second is detached eddy simulation. Third is like scale adaptive simulation. And then there are some modeling like turbulence models, such as one equation model and two equation model. So we can see what these are in very short in coming slides, but make sure that you can go through this equation like continuity and momentum equation. The continuity is change of mass in time and space, and the momentum is movement of the mass in the domain. and variation of the mass with respect to time that is equated to the pressure variation and some stress variation and external forces. So the large eddy simulation is something like we discretize the domain with some given mesh size, and this mesh size basically identified which eddy size can be solved and which eddy size can be modeled. So so this mesh acts as a filter, and you can see here the averaging happens like this is the flow field variable, and we can decompose it into mean and fluctuating part. And the mean part is basically solved over a mesh size using this integral equation. So basically, this solves the compressible Navier-Stokes equations in a transient form over the computational domain. It resolves the eddies based on the mesh size, but the eddies that are smaller than that are modeled with the RANS. RANS is nothing but Reynolds average Navier-Stokes equation, and again the filter size is decided by the operation. Is based on this G filter. So G is nothing but, you can see that the flow field that are solved are basically filtered with this G in the space. So we can have a different approaches to model the smaller eddies that are smaller than the mesh size. And again, to make the problem easier, Reynolds has introduced this average equation. So it is known as Reynolds average equation, where he divided the flow field variable into mean and fluctuating quantity, and then he re-derived the Navier-Stokes equation. And once the equations are re-derived, it introduced 9 extra terms. So identifying these 9 extra terms was a challenge. So therefore, he has used the Bosnick's assumption, where these stresses, we call that as the turbulence stresses, that are equated to the linear rate of deformation through turbulent viscosity. So if you look at any usual viscosity equations, or the usual shear stress equation. So this is tau ij. Then we equate it to viscosity and the change in velocity. Uh, so this is what it happens like. This minus rho vi vj has been modeled with this equation, and this mu t is again a challenging part. And the way we solve this mu t is nothing but with one or two equation, and that has been we call that as a turbulence modeling equations. So these are based on the Navier-Stokes equation that we have discussed so far. There is another method that which is known as lattice-Boltzmann method. So it is mainly based on the Boltzmann's kinetic theory, and it is based on the mesoscopic approach rather than microscopic approach. So Navier-Stokes is based on macroscopic approach, where we divide the flow field domain in a small control volumes, whereas in kinetic theory we divide the domain in a small particle sizes. And based on that approach, we solve these Boltzmann equations. So these particles are solved using particle distribution function over a velocity space using a collision operator. So this equation is famously known as continuous Boltzmann equation. And then a lot of efforts has been put to simplified it in terms of discretized lattice Boltzmann equation. So what it does is like this, Fi is nothing but the PDF in future state, whereas which is equated to the PDF in the present state plus collision operator. And again, collision operator is given by this equation, which is mainly a, a function of the PDF at present state and the PDF at equilibrium state. And once we know the PDF in future state, we can identify its macroscopic properties by summing over the PDF to get the density. When we sum the PDF over velocity space, we get momentum equation. And if we want energy, we can include velocity square space versus on the PDF where we get the energy equation. So there are multiple advantages of Navier-Stokes equation versus LBM equation. Navier-Stokes is very popular. It has been adopted almost by all industries. A lot of commercial option available, like is available, for example, ANSYS, Fluent, Star 15, and there are multiple other companies that are using this Navier-Stokes equations. So they are based on either finite element or finite volume approach, but underlying they are solving the Navier-Stokes equation. They are so the dispersive discretization scheme. So for example, when the noise is produced at say 40 dB, and when it is propagated to the far field, the simulation may disperse the amplitude as well as frequency. So they don't have a very good schemes to very good low order schemes. So if you want to capture the the acoustic signature in the far field, we are supposed to use high order scheme, and that becomes very expensive. And moreover, to capture any frequency, we need to have, like here the example is given. For 200 hertz, the wavelength is almost 170 mm, and to capture these these frequency, we need to have almost 340 grid points uh, in our computational domain to capture the amplitude and the frequency properly. Whereas a lattice-Boltzmann method, although it is known from a long time, it has become popular recently with the commercial option that is available with power flow provided by Dassault Systems. It has relatively less dispersive discretization scheme. So instead of going for fourth or fifth order in Navier-Stokes equation, we can use first or second order scheme to capture acoustics excitation properly. And again, it is computationally cheaper because for a given 2000 hertz frequency, it will require only 12 to 15 grid points compared to 340 points in Navier-Stokes equation. So when it comes to noise propagation in the far field, lattice-Boltzmann method is far more effective than Navier-Stokes equation. So this is the background of the acoustics, how we can model the acoustic source, what are the acoustic source are present, how we can record that noises in test, because for any CFD engineer we use such a high order mathematics. Ultimately, we have been asked to correlate the simulation results with the real life experiments. Therefore, it is very important for any aeroacoustics engineer to know how that test has been conducted, what are the potential disturbances that can be recorded by those microphones. That knowledge is very important when it comes to the correlation part. So here we can look at my PhD problem where I model the radiator fan noise, and then we have compared it with the with the test results also. So here I have used lattice Boltzmann method that is available in PowerFlow. So so the test setup looks like this, where the airflow unit has been placed in a big room, and I have not modeled all the incoming fan and control wall setup here. It is a fairly simplified domain. So the inlet is provided as a planar inlet that the flow enters through this elbow joint, and then it enters in a plenum section where the flow is uniformly distributed inside the plenum using a flow straightener, and then the flow is sucked by the fan. And these circles represent different mesh refinement regions, because we cannot mesh the computational domain with a single mesh size. We need to have some strategies to model the high frequency turbulent sources that are close to the fan with smaller mesh size, and the domain which is not really important, but not really important to capture the sources, but it is important for the propagation of that sound. So based on the frequency of interest, we can choose that mesh size. So you can see that the fan is mounted inside this diffuser duct, and the whole setup has been mounted on a stand where I these parts are not really important to my simulation. That's why I captured it in a very coarse form so that it can represent the setup and act as an obstruction, but it doesn't really carry any weightage in my simulation. And then the fan is placed inside the duct, and the rotation of the fan is modeled using local reference frame. And then there is a gap between the diffuser and the tip of the fan blade, and that with the studies it has been found that that tip gap plays a very important role in identifying the noise levels in the spectra. So if we increase the tip gap, the noise level will increase, and if we decrease the tip gap, the noise level will decrease. So it is important, and the tip gap is very important, so that if there are any deviation from the fans from the center of rotation, so that the blade should not interact with the nearing casing. So a tip gap has to be maintained for that purpose. So and that has been modeled with a very fine mesh. That's why it is marked with this purple region. And we can see the discretization that has been used in this simulation. So as I said, the very important part, that is this tip gap part, is modeled with 0.2 mm, and then the less important parts has been modeled with the coarser mesh size. So the mesh size starts with 0.2 and then it ends with 13 mm inside the plenum. Again, as mentioned, so this 6.4 mm sphere is my is the location where I'm recording the noise, and the mesh size is chosen so that I can model the highest frequency, like up to 10 kilohertz, and to have that, like the requirement is to capture 10 kilohertz wavelength, we should have 12 to 15 voxel in that region. When we look at the noise spectra, so you can see the noise is recorded in front of the fan inside the plenum, and this is the noise level compared with test as well as other methods that has been published in published by other paper. So the black is the experimental levels, and the green is the power flow simulation. And you can see that power flow simulation is able to capture the broadband level properly. There are some subharmonic hums, so this blade passing frequency uh, uh, that is present here, but there are other peaks that are present in between this blade passing frequency. We call that as a subharmonic hum, and that is a result of a tip gap flow structure that has been captured properly, whereas the blade passing frequency, we don't see it. It doesn't mean that the software is not able to capture it. It's just that the simulation is needed to run for longer duration, but my PhD was limited to the identification of the broadband noise sources and the only prediction of the broadband noise. So I haven't run my simulation for longer time, but I have already checked with the Cursor simulation that when we run this case for larger time, we are successfully capturing this tonal peak also. And these are like Flock-Williams-Hawkins method. So this is the direct method that we are comparing. And the brown color is nothing but the Flock-Williams-Hawkins method. The Flock-Williams-Hawkins method is not properly capturing the broadband levels at high frequency region, whereas it is not really capturing low frequency region. But you can see some traces that has been close to the test results in third and fourth region. Whereas PCW is again perturbed convected wave equation that is similar to, I would say, similar to Lee method, and that is also not really useful to predict the noise. So direct method is useful for when we want really an accurate result. But if there are hundreds of DOEs that are present and we want to simulate that and rank different fans, then direct method would be very expensive. In that case, we can use either this Flock-Williams-Hawkins method or other hybrid methods. We can use those methods, rank the fan, and then maybe out of like first 3 to 4 fans, we can take it and we can use the direct method to identify the correct noise levels out of those fans. So I would say the hybrid method most of the time is useful for apple to apple comparison, and then direct method is useful when we want actual result or accurate results from that simulation. So when it comes to the noise source investigation, there are different methods present. So one of the method is looking at vortex formation, because these vortex structure, like vortex structure as well as turbulence structure, that are basically interacting with this blade, as well as they are traveling and hitting the other blade also, and that is creating noise. So these behaviors are responsible for broadband noise as well as subharmonic hums. And this tip leakage is form of different like tip leakage vortex, induced vortex, and tip separation vortex. So you can identify the vortex that is formed from the leading edge of the blade. We call that as a tip leakage vortex, whereas there is a tip separation vortex. So in front of the fan, there is a low pressure or suction pressure, and at the back of the fan, there is a high pressure. So there is always a flow has a tendency to flow from high pressure to low pressure, and that's why the flow try to towards the suction side through this tip gap region, and that's why this tip gap is very important, because this tip gap will determine what type of turbulence level is formed inside this tip separation vortex, as well as size of that tip separation vortex. And this is nothing but a tensor method where we can identify some symmetric and asymmetric part, and then we calculate the eigenvalues to plot these vortices. So when we get this eigenvalues, three eigenvalues, so second eigenvalue, that is called lambda2. So we plot this lambda2 value to visualize the vertical structures in the tip cap region. Another method is we can record the pressure fluctuation on the blade itself, and then we can use band pass filter to look at different frequency region. And here we can see that here we are looking at 300 to 400 hertz band pass, and the color represent the power spectrum of the pressure in terms of dBs. So this surface pressure contours that tells us that near the tip the contribution is higher, whereas when we go away from the tip towards the hub, contribution reduces. And if we look at the spectra over here, we get somewhere in this region the higher peak. So we can correlate that peak with these contour plots, but make sure that this is not directly correlated. This is one of the indication that these surface fluctuations are can be responsible for the noise generation. Secondly, we can use some analytical method to identify the leading edge noise and trailing edge noise sources. So for example, you have some leading edge interaction with the wake coming from the adjacent blade, and then there are some trailing edge interaction due to the wake formed due to this tip vortex. So there are different sources, so you can separate leading edge noise and the trailing edge noise with this analytical method. So EMIAT has come up with some analytical method where you can simplify the problem and take the blade and divide it into multiple pieces, and each strip is modeled as a flat plate, and then the excitation is provided in terms of turbulent in terms of the turbulence parameter, for example, approach velocity excitation, so the velocity variation that is causing leading edge noise, and the trailing pressure variation that is causing trailing edge noise. So based on the type of the based on the location, we can modify the input, and then that excitation is provided to the transfer function return for a flat plate, and then it will give the noise output. And so this transfer function is given by this blue box, and this transfer function is different for leading edge noise and the trailing edge noise. And this SPP tells us the far field noise propagated by leading edge noise and trailing edge noise. I won't go much into the detail, but to go directly jump on to the result is that we can see that the leading edge noise is the dominant one, which is given by this red squares, and the blue squares are basically the trailing edge noise. So in any radiator fan, it is observed that the leading edge noise is again the dominant source than the trailing edge noise. So based on this information, we can modify the design. We can majorly focus on the leading edge, near the leading edge, and we can think about different leading edge solutions. For example, we can provide a sweep to the leading edge. We can add some serration near the leading edge and see how the noise signature is changing. Secondly, the one of the way to look at is the dilatation. So dilatation is nothing but the pressure variation with respect to time in space. So this is so when we use this equation, we can identify the acoustic waves that are propagating away from the fan. And in this case, the center of this acoustic wave propagation usually tells us the source of those noise sources. So this is one of the example for 2800 hertz, whereas this is the example for 7000 hertz. And you can see that the most of the noise or the direction of the noise is coming from the tip region, whereas for the high frequency ones, there is additional source that is coming from the hub region, where some hub region scattering is observed in this plot. So this is how you can use the dilatation to identify from where the noise is coming from. Once we know the correct amplitude of the noise in a far field. So another example is the blower noise. This is the study published by the Powerflow guys when it was EXA in collaboration with Male. It's a German company. It's again a tier 1 supplier for blower. And you can identify, so they're using again the lambda 2 surfaces and coloring with some acoustic power volume density. So it's a different way of looking at the results. But what it tells us that there are noise sources coming from different regions. So majorly the casing and the trailing edge wake interaction, then where the flow starts separating near the lip region. So that region is again important, and again the trailing edge of the blade is also important. So you can have different ways of looking at the problem, and here the correlation is provided. So experiment versus direct simulation versus some analogy they have predicted, and it seems that all these direct and FWH are closely correlating with the experiment results with some deviation.
Hey, DePauli, I hate to interrupt you, but we got about 10 minutes left.
Okay, it's just the last test case, and then give me 2 minutes and I'll finish that. Okay, so so yeah, wind noise is coming from different sources like A-pillar, side mirrors, windshield wipers, tailgate, and all other stuff. There are other sources also from open cavities like sunroof, door gaps, and all those things, and some body sealing issues. So we can again look at wind noise is again aeroacoustic problem, but it is more to that. It's a vibroacoustic problem. So what usually happens is the flow gets separated near the ORVM, and it forms a turbulent wake that basically interacts with the side window, and that window panel is excited by that turbulent flow, and that excitation basically excites the internal cavity, and then the noise propagates inside the cabin. So in CFD, we can identify this turbulent flow interaction. We can use some analogies and identify, or direct method also, to identify noise in outside the cabin. But to identify a noise inside the cabin, we need to use some structural solver, or we can use some transfer function to propagate that noise inside. So these are like multiple application of those aeroacoustic problem. As I said, to become an aeroacoustics engineer, you need to have experience on multiple fronts. You need to have like high resolution CFD simulations. Then you need to know how you can visualize those flow field. Some high order mathematics is involved, some statistical tools, signal processing tools, as well as physics, acoustic physics. The test setup, sensors, information has to be considered, as well as one should have a programming knowledge and noise source investigation knowledge while doing such type of simulations. So these are the usual references if you want to go through. Thank you. Thank you all. I think we are open for the questions if you have any questions.
Excellent. Thanks very much. I'll open the floor to questions from any of our audience. I think Jason has his hand raised. Go ahead, Jason.
Yeah, thank you so much to Pally for the presentation, and thank you, Colin, for the invitation. I got two questions for you. Hopefully, if I'm out of scope, please let me know. I'm curious to see if you're aware of any aerodynamic designs that are resilient against different weather conditions. I say this because some of the higher end electric vehicles I'm aware of, for instance, they will use a lot of channels, for instance, to direct airflows. But I do realize that during the Canadian winters that we have, for instance, that you may have snow build up, which may impact the airflow. So I'm curious to see if you're aware of any aerodynamic tricks that is more resilient in different weather conditions, please.
With respect to noise or just the aerodynamic behavior?
Aerodynamic, but also noise. Yeah, if you don't mind.
Okay. Yeah. If those are like, for example, open cavities. So, can I say that? Of course, like when there is a snow buildup, the flow behavior changes. For example, so if you take Corvette, you have this air diffuser sections for the air intake. If I talk about ICE engines, so there, if you have snow buildup, of course, the air going in through such channels will be affected, and again, the vehicle performance will be affected. But as such, I don't have much example on that part.
No,
I haven't.
sorry. Yeah. Sorry. Go on.
Yeah.
Don't
You
drive in
have
Alberta,
another.
I think is the theme.
All right.
Yeah.
Sorry. Yeah.
Sorry. Go.
No. Please go ahead, Alex. Sorry.
Yeah. Like frankly speaking, like I work from India and now I work for Canoe, California-based company, but mostly we looked at dirt management and the water management, but we never really bother about the snow related issues in the design. So yeah, mostly if it is coming from a field failure, then we usually look at it, but otherwise it's if it is on an exterior and on the side of the vehicle where the shape of the vehicle is drastically modified, yes, during that time the drag will increase and the range of the vehicle will affect in that case. And yes, for electric vehicles it is very important. The maintaining a range is very important. So yes, that is something to be thought about. We look at crosswind thing and its effect on the range, but yeah, the snow thing is not, according to my knowledge, I haven't looked at it, but maybe there are others who are looking at it.
Well,
I'm not
that's
aware
fair.
of it.
Thank you. And the other questions I have is I understand that generally the directions when it comes to vehicle development or component development is generally less noise is better. And I understand that it can minimize impact to other people. And you may maintain a level of awareness on the road. So that's great. But on the opposite, like from a different directions as well, I'm aware that when it comes to electric vehicles, there'll be situations where I believe it's CNIB, the Canadian National Institute for People Living with Blindness, so to speak, they would like to advocate a certain amount of noise level just so that people living with vision loss, that they can still detect presence of vehicles, and also at higher speed. For instance, you probably it will probably make sense to have a certain amount of noise just so they can minimize potentially roadkill or interactions where you hit a wild animal while doing higher speed. And I'm wondering, in your field of practice, is there
Mm.
any scenarios where your design would actually be used to generate a noise for any particular reason?
Yes, that's what the electric vehicles have been come up with some extra source. So we call it AVAS. So that is the added noise source for the pedestrian safety. It sounds like similar to how a subway is passing, but that's one of the example. Yes, we need to add extra source so that pedestrian can be made aware of. And when it comes to the high speed, mostly the comfort is for the people who are sitting inside the cabin than outside the cabin. Um, in that case, like for higher speed, mainly the contributing factors are tire noise and the wind noise. Whereas wind noise is dominantly heard by the people sitting inside the cabin. So that is something we need to tackle and reduce it. Secondly, for the HVAC noise, since the engine noise is gone, so this HVAC noise, when we are running the blower at high speed, that will make a lot of noises. And again, it will be heard predominantly inside the cabin. And for example, you're driving for 5 hours or 8 hours, that will be very annoying. If you switch off your audio system and stay there, right now all the cars are having a very high wind noise, and you cannot tolerate that. So, so that's one of the ways we switch on the audio system and mask the wind noise. But yes, that noise is really bothering people, and now people will start complaining about it. So this is um, the advanced preparation for any OEM to start looking into this wind noise problem and modify the design.
Sounds good. Thank you so much.
I had the same question, Jason. I mean, it's not just blind people. I don't want to get hit either. There's a lot of Teslas and hybrids in the Vancouver region, and at the sort of the lower speeds, sort of say less than 50 kilometers an hour, they're quite quiet, right? There's not a lot of tire noise or wind noise, so that is an issue. I know the Teslas have their crazy UFO sound when they're backing up, but that's not really when they're dangerous. It's when they're traveling at 30, 40, 50 kilometers an hour down a side street and you can't hear them and you step onto the street and you get plugged, right? No one wants that.
Ooh. Thank you.
Yeah, but but now addition of that sound, like it is good for pedestrian safety, but now it is bothering people sitting inside the cabin because
Yeah, you
it's
want a
unwanted.
quiet interior and some kind of
Yeah.
noise in the exterior, right?
Yeah, I think there is I think some certification has to be passed for this pass by noise also. You should have certain noise levels also before, like, yeah, some signature has to be present for this pass by noise certification.
I
So
ride a
yes, it's not.
motorcycle, and a lot of people claim that loud motorcycle exhaust pipes save lives. There is something to that, right? To a
Mhm.
certain extent, and I agree with it. I have a question about the importance of verifying, their model versus testing. You mentioned the high cost of some of the wind tunnel testing, 70 and $80,000 a day, and what have you. Are there some problems that are easier to predict than others in terms of modeling? Like, for example, propellers or blades versus like the mirror on your car or whatever. Are there some certain shapes that are easier to model and you get, close results with testing than others? Are there some cases where you just have to test?
Yeah, for example, like you can predict the noise with this method very well. Only problem is the identification of the noises and modification of that design. So when it comes to this mirror noise, I was able to predict the noise for this mirror, and it was direct. It was direct, like, okay, I need to reduce these turbulence sources and reduce the noise. So, or I can, create some gap between the mirror wake and the side panel, so that we can avoid the direct interaction with the wake. So that is possible. Like once we avoid that interaction, we can reduce the noise. But when it comes to the fan is a very complex system. Although you can predict the noise levels in the far field, identifying what parameters to be modified to reduce noise is challenging.
I guess my
So that's
question
why
is,
I came for PhD.
are there cases where you only need to do modeling, or do you always need to do testing to verify the modeling?
No, usually the method is like you take take some simple geometry, do the correlation, and once you have that method established, you can use that method for any design modification. So you don't have to always go for correlation thing.
Okay. Does
So
anybody else
for
have
example,
a burning question here? We're a little bit over time. Does anybody else have a strong question they want to ask? It sounds like that's it. Well, thank you very much to Polly. We really appreciate your efforts and your time.
okay, thank you so much, Colin, and
And
Neil as well for your time.
we got your email address up there. If anybody has any follow-up questions, we will try to post that in our next SAE BC newsletter so they can follow up with you directly.
Okay, sounds good. Yeah, you can write to me anytime. I'll be glad to reply all of your questions.
Okay, well, thanks everyone for joining us. Thank you very much to Polly.
Thanks to Polly. Yeah, good luck for the rest of your day.
See you, everyone.
Thank you.
We will see you all next time.
Okay.
Take care,
Have
everyone.
a good evening.
Take
Bye
care.
bye.
Stay warm.
Bye.
Safe. Thank you.